Okay, have you tried this example, or anyone can tell me what we need to do? So for this example, we need to construct the stiffness matrix for the global stiffness matrix for this truss. So this truss consists of two elements, member 1 and member 2. So member 1 is starting from node 2 and end with node 3. The degrees of freedom at node 1 are 1, 2, 3, 4. Member 2 is inclined member with starting with node 2 and end at node 1. The degrees of freedom for member 2 is 1, 2 at node 2, 5, 6 at node 1. What we need to do is construct the stiffness matrix for member 1, construct the stiffness matrix for member 2, and then combine together to find the global matrix for the whole structure or the whole truss. Okay, so I will start sharing my whiteboard screen and start with member 1. So first step is to find K for member 1. Member 1 is a horizontal member. Just start with, and this is the direction of the member. Start from node 2 and end with node 3. The degrees of freedom at node 2 are 1 and 2. The degrees of freedom at node 3 are 3 and 4. Okay. Again, this is our local axis for this member. And this is our global axis for the whole structure. What is the relation between global axis and local axis for this one? And for this element, because it is a horizontal element, so the axis will be concise. So the local and the global axis are similar for this one. Okay, anyway, we will go step by step for this one. If we go back to the previous slide, what is the global stiffness matrix for truss element? Equation 15. So what I will do is just write it down. Okay, so K, as you know, is AE divided by L, sigma x squared, sigma x, sigma y, negative sigma x squared, negative sigma x, sigma y, sigma x, sigma y squared, negative sigma x, sigma y, negative sigma y squared, negative sigma x, sigma y, negative sigma y squared, sigma x, sigma y squared, and here negative sigma x, sigma y, sigma x squared, and sigma x, sigma y. Okay, so to start substituting here, we need some parameter. A and E are not given to us, but we know L. What is L? L is the member length. From this example, the member length is given to us as 3 meter, 3 feet. So you can see that the member is 3 feet. So we know the member length is 3. We need also sigma x, lambda x and lambda y. Lambda x is equal to cosine theta x. Lambda y is cosine theta y. Okay. Anyone can tell me what is theta x and what is theta y? If this is a horizontal member, so theta x is equal to 0. Theta y is this angle which will be 90 degree. So because it is horizontal member, so no angle with x axis, so it will be 0. And the angle with y axis will be 90 degree. Okay, so lambda x will be cosine 0 and lambda y will be cosine 90. Cosine 0 is equal to 1. Cosine 90 is equal to 0. So if we substitute in K1 now, K1 will be equal to AE divided by 3 times the displacement are 1, 2, 3, 4. And here 1, 2, 3, 4. So 1, 2 is the deformation at node 1, 1 and 2. 3 and 4 are the deformation or displacement at node 2, at node 3, 3 and 4. So this is how we number the matrices elements. Okay. For your information, anything will be multiplied by lambda y will be 0 because lambda y is equal to 0. So we are looking for only members with lambda x. So here, this will be 0, 0, 0, 0, 0, 0, 0, 0. All this member will be 0 because they are multiplied by lambda y. So the only elements we will have in this elements or this is truss element are with theta x squared. So we will have, and theta x is equal to 1. So we will have 1, 0, negative 1, 0, 0, 0, 0, 0, negative 1, 0, 1, 0, 0, 0, 0, 0. Okay. So this is the truss, the stiffness matrix, the global stiffness matrix for member 1. Global stiffness matrix for member 1. Okay. Now if we go to member 2. For member 2, we need to calculate K2. K2 is an inclined member. This is a general case we were studying before. So this is our member 2. Member 2 start with node 2, end at node 1. The displacement or the degrees of freedom at member 2 are from previous 1 and 2. And here from previous step is 5 and 6. Okay, again, this is our global axis and this is our local axis. Okay, so for this member, again, we know that we need to know L, length of member 2, lambda x for member 2, lambda y for member 2. To know lambda y for member 2 or lambda x for member 2, we need to find the angle. So the angle here, this is theta x and this is theta y. And we need also to know the length. So from the given data, this is given as 3 feet. This is given as 4 feet. So the length of member 2 is 5 feet. How can we find this? L2 will be root 2 squared plus 4 squared. So it will give us 5 feet. Okay. Theta x lambda x2 is equal to cosine theta x, which will be 3 over 5. Lambda y will be cosine theta y, which is equivalent to 4 over 5. Okay, if you complete this triangle here, so you can find theta y. This triangle is theta x. So 4 feet, 3 feet, 5 feet, you can find theta x. 4 feet, 3 feet, 4 feet, 5 feet, you can find theta y. Anyway, theta x, cosine theta x will be 3 over 5. Cosine theta y will be 4 over 5. So if we revise the equation again, AI over L. What is L? L is 5 meter times theta x squared, theta x, theta y, negative theta x squared, negative theta x, theta y. I will write only the top part. So this is lambda y squared. Okay. And this is lambda x squared. This is lambda y squared, negative lambda x, lambda y, and negative lambda y squared, lambda x, lambda y. Okay, so to construct the K2, we have A E over 5. Before we start, what is the degrees of freedom, or what is the displacement we have? At node 1, at node 2, sorry, to start here, we have degrees of freedom 1 and 2. So this will be 1, 2. Here we have 5 and 6. So 1, 2, 5, 6. 1, 2, 5, 6. So 1 is theta x squared. What is theta x squared? Sorry, lambda x squared. What is lambda x squared? 9, 3 over 5 squared. The next one is 3 over 5 times 4 over 5. Negative 3 over 5 squared. Negative 3 over 5 times 4 over 5. This one will be 4 over 5 squared. Negative 3 over 5 times 4 over 5. Negative 4 over 5 squared. 3 over 5 squared. 3 over 5 times 4 over 5. And finally, we have 4 over 5 squared. Okay, and this part is symmetric with this part. Okay, so now just to figure out what is K2 now, K2 will be AE over 5, 1, 2, 5, 6, 1, 2, 5, 6. So it will be 9 over 25, 12 over 25, negative 9 over 25, negative 12 over 25, 16 over 25, negative 12 over 25, negative 16 over 25, 9 over 25, 12 over 25, and finally 16 over 25. This one will be 12 over 25. negative 9 over 25, 12 over 25. Okay, this one will be negative 12 over 25. This one will be negative 16 over 25, negative 12 over 25. So this is the final global stiffness matrix for member 2. What is our next step after we get global stiffness matrix for member 1 and the global stiffness matrix for member 2? Do you have any idea? I will just for make it easier for us to calculate. I will write down here K for member 1. What we got for member 1, AE over 3 times 1, 0, negative 1, 0, 0, 0, 0, 0, negative 1, 0, 1, 0, 0, 0, 0, 0. And what is the numbering of degree of freedom for this one? This is 1, 2, 3, 4. 1, 2, 3, 4. So what is the common, or how can we assemble the global stiffness matrix for this one? The common members here is this 4, 1, 2, 1, 2, 1, 2, 1, 2. So here also 1, 2, 1, 2, 1, 2, 1, 2. That's why we're starting with 1, 2 for both of them. So if we can combine this together, so we can, this is the start for our global stiffness matrix. Okay, so how much our global stiffness matrix firstly? Okay, after this we need to find, using these two, using these two members, we need to find K capital global for the whole structure. K capital global for the whole structure will be 6 by 6. Why 6 by 6? How many degrees of freedom we have? This is our truss. So we have here 1, 2 degrees of freedom. Here 3, 4 degrees of freedom. Here 5, 6 degrees of freedom. So our stiffness matrix, global stiffness matrix for the whole truss is 6 by 6. So if we try to do this here, we will have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They will write so the first member is 1, 1, 1. So where we can find 1, 1? Here is 1, 1, and here is 1, 1. So this one will be 1 plus 9 over 25, which is 34 over 25. The next one is 2, 1. 2, 1 is this two elements, this one and this one. So it will be 12 over 25. The other one is 1, 2. here 0, so we have 12 over 25. Here is 2, 2, and 2, 2 here, so we have 16 over 25. So this part is the most important part of the stiffness matrix, because this part has common elements in global matrix for member 2 and the global matrix of member 1. Now, here, this is member 3, 1. Do we have any 3, 1 member? This is 3, 1. Do we have 3, 1 member? Where we will find 3, 1 members? Here in this element, in element 1. Because we have only 3 and 4 in member 1. So you can find only member from member 1. So we will have from here. So 3, 1, we have 3, 1, we have negative 1. 4, 1, we have 0. 3, 2, we have, this is 2. 3, 2, we have 0. 4, 2, we have 0 as well. Here, we have 1, 3. 1, 3, we have negative 1. 1, 4, we have, sorry, 2, 3, we have 0. 1, 4, we have 0. 2, 4, we have 0. Okay. 3, we have here 3, 4, 3 and 4, 3 and 4. So we have 3 and 4, this 4 members. So 1, 0, 0, 0. Okay. Now 5 and 6. 5 and 6, we have 5 and 6 only in member 2. So we have 5, 6, 5, 6. So 5, 1. Do we have any 5, 1 member? We don't have any 5, 1 member. Or we have here 5, 1. So negative 9 over 25. Here 6, 1 member. So this one is negative 12, 25. 5, 2 member. So we have negative 12 over 25. 6, 2 member. We have negative 16 over 25. Okay. Here as well 1, 5. So this member negative 9 over 25. 2, 5 member. So negative 12 over 25. Here 12 over 25. 2, 6 is negative 16 over 25. Okay. So now we have just 6 members. The remaining 6 members are 3, 5, 4, 5. Do we have any common thing between 3 and 5, 4 and 6? 3, 5 and 6 are in member 2, 3 and 4 are in member 1. So there is no common thing in this member. So 5, 3, we don't have any coordinate called 5, 3. So this will be 0. 6 and 3, 0. 5 and 3, 5 and 4, 0. 6 and 4, 0. Here, 3 and 5, 0. 4 and 5, 0. 3 and 6, 0. 4 and 6, 0. 5 and 6 and 5 and 5, we have them here, this corner. So 5, 5 is 9 over 25. 6, 5 is 12 over 25. Here, negative 12 over 25. Here, 16 over 25. Okay. Do you have any problem to construct this global stiffness matrix? Do you have any problem? Okay, so this is how to construct the stiffness matrix for the whole structure. It looks like a big procedure, but it is simple. We will simplify it in the next slide. But this is how to construct the global stiffness matrix for the whole structure. You need to construct it for member by member, and then after this, you have to construct one by one, and then we have to assemble them together. Okay. Okay. We'll have another rest for 10 minutes and we'll be back. Okay. If you can just again. If you can think about, try how to do it yourself, and let me know if you have any question, and I can repeat. Okay. Thank you.
例子你要跟着先做，对吧？不要等到最后，光去听没有用。它这个例子本身很简单，你要是光看的话，就是很易，你自己动手做一做。
Okay, guys. So, are you okay back to continue? Are you good to continue now? Can you see my screen? Okay. So for this example, we have learn how to construct the global stiffness matrix for the whole structure using the global stiffness matrix for each member. Okay. And now need to learn how to get the, if after constructing the stiffness matrix, the global stiffness matrix, how to get the unknowns, the displacement, and the forces Q. So once the structure stiffness matrix K capital is formed, this is the one we have already done. We can then use it to determine the joint displacement and external forces reactions and internal member forces. So joint displacement are D capital, the vector D capital. External forces and reaction are Q capital. Okay. As we have always assigned the lowest code number to and define the unconstrained degrees of freedom, this will allow us to partition Q equal to QD in the following form. QK and QU equal to K11, K12, K21, K22, DU, DK. Okay. If we go back here, what is the degrees of freedom we have from 1 to 6? But some of them known and some of them unknown. The unknowns are 1 and 2 because this is a free joint or a free node and it cannot, and it can move. But for node 3 and node 1, we have 4 degrees of freedom, 3, 4, 5, 6. These 4 degrees of freedom are equal to 0 because they are restrained. Sorry, they are restrained by the support. Okay, so in our trust analysis using stiffness method, we have some displacement are known and some displacement are unknown. The unknown displacement here is 1 and 2. The known displacement are 3, 4, 5, 6. If we go back to here, what we will do is just partition or divide the stiffness matrix and the displacement and the Q force Q vectors to known and unknown, just to make it easier and more simplified. Otherwise, we cannot deal with a 6 by 6 matrix. 6 by 6 matrix is too big to deal with manually. So that what we will do is just subdivide the stiffness matrix to make it easier for calculation. Okay. What we will do is divide the Q matrix to 2 parts, QK and the QU. QK and the QU, sorry, QK is the known external forces, which means the applied loads. QU is the unknown forces, which is the reactions. Okay. DU is the unknown displacement, which is 1 and 2 in our case. DK is the known displacement, which is 3, 4, 5, 6. So as you can see, QK is in same line with the unknown. So the unknown displacement can be found using the known loads, and the unknown loads can be known or determined by the known displacement. So here, QK and DK are the known external forces and displacement. The load here exists on the truss as part of the problem, and the displacement are generally specified at 0 due to supports. What is meant here is 2K is our load, 3, 4, 5, 6 are 0 because of the supports. Okay, so to continue, QU and DU are the unknown, so U are the abbreviation for unknown loads and displacement. The loads here represent the unknown support reactions. So QU is the unknown support reaction, DU is the unknown displacement at joints. Okay, if we expand equation 16, so QK will be K11 DU plus K12 DK, and QU will be K21 DU and plus K22 times DK. Most often DK are equal to 0 because the supports cannot move, so we can write the above. If DK is 0, so the second term in both equation will be 0. So to find Q, so or we can write QK as K11 DU, and QU will be equal to Q21 times DU. Okay, so this is in our calculation. Mostly DK is 0. The only case that D can has value is if there is settlement at the support, or pre-assigned or predefined deformation of the support. Other than this, if the support is normal, so there is no movement. Okay, so mostly this will be 0. So now QK equal to K11 DU. So to find DU, we need to find K11 minus 1 times QK. So K11 minus 1 is the inverse of K11. So what we need to do is get the stiffness matrix K capital, then subdivide the stiffness matrix to K11, K12, K21, K22, and then after this we have to get the inverse of K11. Okay, so as QK is the matrix of the known displacement, sorry, the known applied loads, so equation 18 can be rearranged as follows: du equal to K11 to the power -1 times QK. From this equation, we obtain the direct solution for the unknown joint displacement because we know QK, the known loads, we know K11, the stiffness matrix, so we can get du. Okay, so the other one is QU. To find the reactions, QU equal to Q21 times du. So this is to find the reactions. From equation 20, the unknown support reaction can be determined. So we can get QU. So our first step is to find du from step or equation 19. Then using du in equation 19, we can find QU in equation 20. Okay, and if you return back to the previous lectures, we mentioned that the stiffness method depending on calculating the displacements, and then using the displacements, you can find the reaction forces, strains, stresses, and so on. So this method depend on getting the displacement at the first step, and then using the displacement, we can get the loads and the stresses. Okay. From equation 10, the member forces can be written in this. This is just to simplify the process to find the forces. So the member forces can be determined using equation 10. From equation 10, you can find that Q small equal to K dash times T times D, where K dash is the local stiffness matrix, T the transformation matrix, D is the displacement matrix in global system. expanding this equation will give us Qn, Qf equal to AE divided by L times 1, -1, -1, 1, and so on. So equation 21 can be written to get a relation between the local forces and the global displacement. Okay, so if you know the global displacement, so you can get the local forces. This is another way to get the forces. Okay, so since Qn equal to negative Qf, because they are in opposite direction, because it's a truss, so in truss, the forces should be in equilibrium. So if one positive, the other one will be negative. If the one negative, the other one will be positive. So for equilibrium, Qn is equal to negative Qf. So one force is enough to find the, we need only to find one force, and the other one will be the negative sign of it. So Qf will be AE divided by L times negative lambda x, negative lambda y, lambda x, lambda y times dnx, dny, dfx, dfy. Okay. The sign convention is if the force is positive sign, so this means it is tension force. If the force is negative sign, so this is compression force. Okay. So can you understand this one? So QF will be equal to AE L divided by negative lambda x, negative lambda y, lambda x, lambda y, d times dnx, dny, dfx, dfy, where QF is the local or the forces, member forces in local system. Negative lambda x, negative lambda y, lambda x, lambda y is the product of these two matrices on the first in the previous step, which is k dash times t, and dnx, dny, dfx, dfy is the global stiffness matrix. Sorry, the global displacement vector. Okay. Do you have any question for this one? Do you have any question? So I just go back to this step again, just to explain it to you. Okay. In our previous example calculation, we get K, where K is the global stiffness matrix for the whole structure, which can be divided into 4 matrices: K11, K12, K21, K22. Okay. The main part of this K is K11. Okay, so we are looking all the time for this one. This is our important one because our displacement are depending on this one. So if we have a look here, our general equation for stiffness method is U equal to K times D. So using this subdivision, we can write it as Q K Q U. Q K is known, Q U is unknown. Equal to K11, K12, K21, K22 times du dk. Okay, most of the time dk, the known, are 0. So if this is 0, so this is make it easier for us. So q k, how to find qk? It will be first row in first column, then second row first column. So it will be QK equal to K11 DU plus 0 plus K21 DU plus 0. So QK equal to K11 DU plus K21 DU. Okay, sorry, there's a mistake here. Okay, QK and QU. QK will be Q11 DU plus K12 DK. This is our first element. Second element will be QU equal to Q21 DU plus K22 DK. Okay, DK is equal to 0 because this is a restraint from the support, and the support prevent the movement. So we can replace K, DK with 0. So this equation become QK equal to K11 DU, QU equal to K21 DU. Okay, for the first one here, we know Q and we know K1 and we are looking for DU. In the second one, after we know DU, so we know DU, K22, K21, and we are looking for Q1. So our first step will be to find DU, the unknown displacement. We will need to find K11 -1 times QK. This is our general equation, I. K11 is called or we can get it from the global stiffness matrix. Du is the unknown displacement. Qk is the known applied load. So from step we can get du. Second step is to use this du and get q ultimate, q unknown. So q unknowns will be equal to K21 times du. This is equation number 2. Okay, so Qu is the unknown reactions, du is unknown displacement. We calculate them from the previous equation, and Q21 is from the stiffness matrix, this one, and Q11 is this one. So this is the importance of the stiffness, the global stiffness matrix. using the global stiffness matrix, and after subdividing the global stiffness matrix, we will need K11, K21. Using K11, we will get the the unknown displacement. And using the unknown displacement, in the next step, we can find the unknown reaction. Okay. Do you have any question about this equation? No? Just a quick last thing we will do today is, if you go back to the example we have done, I just open the bind file. Can you see the screen? Can you see my screen? Okay. So now we just need to know how to subdivide this one to K11, K12, K21, K22. If we have the global matrix, so how can we subdivide it to K11, K12, K21, K22? Okay. So now, for this truss, this K, it was 6 by 6. So if you remember the truss, this was the truss member. This was node 1, node 2, node 3. The degrees of freedom was 1, 2, 3, 4, 5, and 6. Okay, so we have 6 degrees of freedom. That's why it was 6 by 6. Okay, what are the unknown displacement du? Du are 1 and 2. What are the known displacement dk? dk is 3, 4, 5, 6. dk's, all of them are 0. 1 and 2 are unknown for us. Okay, using these two information, we can subdivide the member, the global stiffness matrix. So I will write it down again here. We have 1, 2, 3, 4, 5, 6 members. So we have 34 over 25, 12 over 25, negative 1, 0, negative 9 over 25, negative 12 over 25. So this 1, 2, 3, 4, 5, 6. Here is 12 over 25, 16 over 25, 0, 0, negative 12 over 25, negative 16 over 25, negative 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. We have negative 9 over 25, negative 12 over 25, 0, 0, 9 over 25, 12 over 25, 12 over 25, negative 16 over 25, 0, 0, Negative 12 over 25, 16 over 25. Okay, so this is our 3, 4, 5, 6. This is our global stiffness matrix. How can we find K11? K11 will be the corresponding to the unknown degrees of freedom or unknown displacement. So 2 and 1. So any member has the name or the order of 1 and 2 will be in K11. So it will be 2 by 2 because how many degrees of freedom we have? 2. So K11 will be 2 by 2. Okay. So K11, it is the unknown stiffness or global stiffness matrix. So it will be 2 by 2. And it contains degrees of freedom 1 and 2. So if we go here, so this is the 4 member we are looking at. So this is K11. So K11 will be 1, 2, the elements with the order 1, 2, 1, 2. So it will be 34 over 25, 12 over 25, 12 over 25, 16 over 25. Okay. Anyone has any question about this? So this is K11. So where is K12? If this K11, so this is K12. And this is K21. And this is K22. Okay. So the main thing we need to know is K11 and K21. K11, we can get it from the degrees of freedom. So we have degrees of freedom, unknown degrees of freedom 1 and 2. So using the unknown degrees of freedom 1 and 2, we can know K11. And K21 is elements under this 2. So it will be K21. This one is 4 by 2 element by 2 stiffness matrix. So K21 is 4 by 2, and it will be equal to, or what is the number first in this one? What are the order? The orders of these elements are 1, 2, 3, 4, 5, 6. So the order will be 1, 2, 3, 4, 5, 6. Where 3, 2, 3, 4, 5, 6 is the known displacement. Okay, so it will be 1, 2, the unknown displacement in columns, and 3, 4, 5, 6, the known displacement in rows. So this will be -1, 0, 0, 0, -9 over 25, -12 over 25, 12 over 25, and -16 over 25. Okay, so now we know K11 and K21. So using K11 and K21, what can we do using these two? If we go back to the slides. So using K11 and K21, we can find the unknown displacement du and the unknown reaction qu. Okay, do you have any question for this one? I will give you a practice to do and show me next week, or if you can send me by email. If you can try to find the forces in this truss after we get K11 and K22. So if you can do this, and I will send you in the WeChat the updated dates for submission the assignment. So we'll send you today or tomorrow. And if you have question, please let me know. And do you have question today? Any question for today? Okay, all good. I just share with you the what is the best way to send you the recording?